The next talk is non-rational toric geometry 3, Quasifold, Foliation, Combinatory, and one-parameter family by Fiametta Battaglia from Universita degli Studi Firenze.
So, hello to everyone. Good morning, good afternoons, good night. So, thank you very much for the invitation again to speak in this conference. It's a great opportunity. So, today I will continue my survey. And so, so let me synthetically remind you what I've been talking in my last talk. So even people that did not attend can follow what I will say in the sequel. So, okay. So. I was concentrating on this, feature of toric geometry. So where we have a rational fan, which is I'm repeating myself, but just for 5 minutes. So you will have maybe. Someone will be bored, but I think it's useful. So in toric geometry, we have a rational fan, which is a convex geometric object. And this determines a toric variety, which is a complex geometric object. So I've concentrated on polytopes in my first talk. And in this talk, I will talk about, I will consider fans, so we won't get confused between the two objects. And we have seen in the previous talks by Elisa, Prato, and myself that this correspondence was first generalized to the non-rational setting by Elisa in the Prato in the late 90s. In the symplectic simple case, and then this was extended by successive works. So we have this non-rational setting, and as I already remarked, there are key ideas in this first paper by Elisa Prato that are essential and fundamental for the non-rational setting in general, I mean. And one of these key ideas is to consider on the convex geometric side as a starting object a triple where delta is either a fan or a polytope. Q is a quasi-lattice, and there are vectors that are in Q and are generators of the fan rays. If delta is a polytope, we consider the fan normal to the polytope. And the fan is said to be quasi-rational, a quasi-rational fan with respect to the polytope, the quasi-lattice Q. So we have this non-rational setting, and let me make some remarks. So, still repeating myself. The first remark is that we have such a triple in the rational case as well, because whenever we say non-rational fan, we always mean in toric geometry, say in the classical situation, we mean a fan together with a lattice, the lattice with respect to which the fan is rational, and there is a canonical choice of vectors that are the primitive vectors with respect to the lattice, primitive rays generators. And so we do have such a triple that is used in the construction of the corresponding toric variety. So the other remark is that even though Elisa PRATO considered polytopes, it is really immediate, and to transfer these notions of this non-rational setting to fans. And in fact, these notions mainly concern the fan that is normal to the polytope, and quasi-rational fans are explicitly considered, for example, in these papers of mine on Betty numbers, or this other one on the non-complex, non-simple case, in these articles with Dan Zaffran, and in this latest article with Elisa, PRATO, and Dan Zaffran. So it's really, there is no difference as much as the non-rational setting is concerned in considering polytopes or fans. It's really, there's no difference. So, and so in our previous talks by Elisa and myself, we have seen that in non-rational toric geometry, a non-rational triple, so when Q is not a lattice, determines a toric stratified space by quasifolds that is in fact a toric quasifold in the simplicial polytopal case. Okay, so this is what we have seen so far. So, and then I want to present a development of these ideas and the motivations. Main motivations were that toric quasifolds and toric stratifications by quasifolds are, you know, they have great features. They are explicitly constructed, they are very concrete spaces, and share key features with their non-rational counterparts, with you know, classical toric varieties. In particular, for example, they are compactifications of quasi-tori. Quasi-tori have been defined by Elisa in her first paper, and are and she defined them in detail in her talk. So, on the other hand, these spaces are, you know, naturally highly singular as topological spaces. We have seen that they are non-Hausdorff. So it is natural to ask if there exists a kind of desingularization, meaning that if there exists a framework that allows to work with smooth objects. And so this is a natural question that arises from these constructions. And another say context is that I already mentioned in my earlier talk, is Stanley's proof of the g-theorem. We have seen that this relies on a reduction argument to the rational case, and then it is based on the link between combinatorics and of the fan and topology of the associated toric variety. So it is natural to seek for a proof that avoids this reduction to the rational case and that unifies the rational and non-rational cases. So with these motivations in mind, with Dan Zaffran, we introduced, we introduced a new framework in which we could see toric quasifolds, and so what I think was at the time a new viewpoint in non-rational toric geometry, and the archive posting dates back to 2011, so it's quite you know, some years ago. And to develop this new framework, as always, when does, I mean, we built on and was inspired by two previous articles. So it's good to make some history on how ideas develop. So the first one is the first article by Elisa Prato that I mean, I already mentioned, and that she talked about in the first talk of this mini course. And then there is this article by Meersseman and Verjovsky that Alberto talked about in his talk, but I will say a few things about this because it's the first time it's mentioned in these I mean, in our talks. And of course, our construction owes a lot also to other previous works. And so let me say something about the article by Meersseman and Verjovsky, which is, as I said, was very inspiring for what we did, because, well, let's say just what they did, and then I'll comment on this. So as Alberto told us, and it was really great to hear the history from Alberto, LVM manifolds originated in the context of dynamical systems. So quite something that seems far away. And they were introduced by Lopez de Medrano, that I've seen in the audience, and by Alberto Verjovsky himself in 1997, and then further generalized by Meersseman in 2000. And these LVM manifolds form a large class of compact, complex, non-Kähler manifolds that admit a holomorphic foliation. And this was established by Nicolau and Meersseman. This is a very short kind of history. And as far as we are interested in this talk, let me say that by combining Gale duality with symplectic reduction, Meersseman and Verjovsky established a correspondence between LVM manifolds satisfying a rationality condition and simplicial projective toric varieties. So precisely and in particular, they prove that if we have a simplicial projective toric variety, then there exists an M, an integer M greater than 0, and an infinite family of LVM manifolds, such that each member of the family is a generalized Calabi-Ekman fibration over X delta, the original, the starting toric variety, with tori of complex dimension M as fibers. And when the toric variety is smooth, is not, has not finite quotient singularities, the fibration is a principal holomorphic bundle. So as I said, this was really inspiring for us, because in this paper one can see that toric varieties can be seen as leaf spaces of compact complex manifolds endowed with the holomorphic foliation. So we put together this viewpoint with what we knew on the non-rational setting. The non-rational setting was ready, complex toric quasifolds were there, and all the ideas were there for the non-rational setting, and so it seems to be a good idea, and to build on these two different circle of ideas. So let's see what we did then. So the first thing is I want to look at is the convex geometric side of the problem. So we have seen that a natural starting datum is the triple that was introduced by Elisa Prato. And so we have now delta is a complete simplicial fan in Rd. D is now the dimension of the space. And the vectors are generators of the fan rays, and they belong to the quasi-lattice Q. This is the starting datum, and this will be the starting datum. But we encode this datum in a triangulated vector configuration that we require to be odd and balanced. So I'd like to explain what is this, so what is this object, and also why we do this. So what is this? This is a pair V T. V is a vector configuration. It is a list, simply a list, an ordered list of vectors that live in Rd. We can allow repetition, and this list of vectors is balanced. This means the sum of these vectors is 0 and odd. So the difference between the number of vectors and the dimension is odd. And as we will see, these conditions are not at all restrictive. Okay, so this is V, the first term of our pair, the first item of our pair. The second item is a triangulation T of the configuration V. It is a collection of subsets of 1n that we call simplices that satisfy certain conditions. So the notion of triangulated vector configuration, and this is very well known, and it was already present. It was already studied and present in the literature, especially in combinatorics. So it's a well-known combinatorial object that allows us to encode the triple on one side, and that is instrumental to the context we are working in. So this is why we have chosen to chosen such pairs, because they are existing objects in literature. There is a whole theory that treat these objects, and they are, as I said, they are instrumental to what we want to do. So how do we encode a triple in such a pair that is also a very neat object? Is very simple. So so let's see. We have to check a couple of things. So we have this list of vectors already in our in the Prato's triple, V1, VH. So if they span the quasi-lattice, and if moreover they form an odd and balanced vector configuration, then we keep the vectors as they are, and V is going to be the list of V1, VH. If this is not the case, we can add ghost vectors so as to have a set of generators of the quasi-lattice. So we might want to add generators of the quasi-lattice Q and add vectors so as to obtain an odd and balanced configuration. And let me remark that in the paper by Meersseman and Verjovsky, they have this procedure of adding vectors in order to get a set of vectors that are generators of the lattice. Here we are in the rational case that is balanced and odd. And these additional vectors correspond in the language of the paper to indispensable points. So so we have seen, we were saying how we encode a Prato's triple in this pair. So V takes care of the vectors and of the quasi-lattice, while T is determined by the Fan combinatorics. So T is the combinatorial datum, the pure combinatorial datum, okay? And T together with V encodes always, whenever we have this kind of datum, encode a complete simplicial Fan, raised generators, a quasi-lattice Q, and a number of ghost vectors that are those that are not indexed by the triangulation T. So in short, just to see in short what's the relation with what we've been describing up to now, if we have a Prato's triple here, we can encode the triple in a triangulated vector configuration like this, which is essentially the triple plus some additional vectors. And the arrow is dashed here because there are many such triangulated vector configurations that encode the same triple. Okay, so now we'll see in a moment why we you know, it's in this context it's good to have such a combinatorial object. So we wanted to consider, we wanted to say work on the non-rational setting with non-rational simplicial fans, but in general. So we don't not necessarily polytopal, I mean. So we use a generalization of LVM manifolds that is due to Frédéric Bozieux. So in his construction, the starting convex geometric datum is a pair made of lambda T star, where lambda is a set of points in CM, and we have also a combinatorial datum T star that is based on this list of points, and that satisfies one geometric condition and one combinatorial condition that are detailed in this slide, but I don't want to go into these details. They satisfy two conditions. The first geometric and the second combinatorial, A and B, we call them A and B. And this pair can be reinterpreted again in terms of non-convex and combinatorial objects that are, you know, studied in combinatorial, in literature in combinatorics as the triangulated vector configuration. So lambda is an ordered list of points in a fine space. We call it a point configuration in CM. Considered as an affine space, and T star with conditions A and B is said to be a virtual chamber. Sorry, I'm looking at the watch on my side now and then. Okay, so we have this, this pair, and now Gale duality comes to help us, because by an old result, we know that balanced vector configurations are in Gale duality with configurations of points in a fine space. So we have this relation that is Gale duality, where the right arrow is dashed since the point configuration is determined up to R linear affine automorphism of CM. So it's, and this is because, you know, when we really construct, we really say by hand, we compute Gale duality, we make choices. We make choices also on the reverse, with the reverse arrow, but this is give ambient isomorphic vector configurations, so it's all right. So T star is determined completely by T and vice versa. And we proved with Dan that T is a triangulation of V if and only if T star is a virtual chamber of lambda. So with this, you know, correspondence given by Gale duality, we are able, so let's put this correspondence just a second on we have that. Then what happens if we consider a pair lambda T star, then we can construct a manifold, complex compact manifold, that an LVMB manifold actually. So as usual, as always happens, I mean, we have seen many incarnations of this construction. T star, the combinatorial datum, gives us an open subset that is here an open subset of CP to the n-1. We have seen already this in Alberto's talk. And lambda, this point configuration, gives a CM action on this open subset that we can write in this way. And we have also seen this in Alberto's talk. And we have that Bosio's conditions we have seen and proved that hold on this pair lambda T star. Moreover, this action is free. And therefore, the orbit space is a compact complex manifold N. So we call this manifold N. I know that in my previous talk, N was a group, the group that was introduced by Elisa in her first talk to construct symplectic toric manifolds as symplectic reductions. But this is done on purpose, and because you know, these notations are you know, have a history behind them, and I think it's good that people can recognize object through the literature. So N in the non-rational, in Elisa's article, comes, if I'm not mistaken, from Delzan's paper in the Delzan construction, and stands, I think, for nucleus kernel, and is the kernel of comes from from a projection map that I heard is in some other articles is known as calibration. So N is a group in that context, but N in LVM theory is the manifold. And so we thought it was good to keep both notations. So I'm wasting my time with comments, but so I'm going to be a little bit faster maybe. So we have this compact complex manifold, and we have a foliation on this manifold that is induced again by this configuration lambda. So we have this other CM action on the open subset that commutes with the first one that we have defined, so descends on the manifold N. And since the isotropy is a discrete subgroup of CM, this action induces on N a holomorphic foliation of dimension M. This was classical already in LVM theory, and this viewpoint we used to this kind of way of writing this action. We took it from Ustinovsky, and in the context of moment angles manifolds that have been treated in the previous two talks today. So what can we say about the leaves? The leaves of this foliation. So the leaves can be, the topological structure of the leaf depends on a kind of rationality measure of the configuration. So here is just, I just for simplicity describe the generic leaf, and you see that the generic leaf can be a compact torus in the rational case, but can be can be also a product like this, or be simply R to the power 2m in the totally non-rational cases. And we can have all the, you know, combinations in between. This is the closure of the leaves. And these numbers can be also defined directly on the configuration of points, and in particular A was already defined by Meersseman, and it is the upper bound of the algebraic dimension of the manifold N. Okay, so finally we have this diagram. So we have Prato's triple as a starting object, then we encode this in a triangulated vector configuration, and by Gale duality we obtain a pair lambda T star. So on one side we have that the triple determines a complex toric quasifold of dimension D, and on the other side, for every choice that we make in this with these dashed arrows, we obtain an LVMB manifold that projects onto the toric quasifold. The toric quasifold is exactly the leaf space of N. So I explained already why the arrows are dashed. So the biholomorphism can be written explicitly, the projection. And as in the rational case, the topological type of the leaf depends only on the rationality measure, as I explained. But when we vary the choice of Gale dual, you see that the complex structure of the leaf space remain constant, but the complex structure of the leaves varies with Gale duality. Okay, so we have this picture. So I think now, yeah, okay, I just wrote a precise statement of this. Okay, so starting with the triple, we obtain a family of LVMB manifolds, and for each of them, the leaf space is biholomorphic to the corresponding toric complex quasifold. And in the rational polytopal case, we reobtain the result that was of Meersseman and Verjovsky. Okay, so now I think I have prepared some examples, but it's a bit, I don't think, I mean, it would be good to go through the examples with a calm and in details, but I don't have the time. So I just want to stress again that the fan of CP1 is a great source of examples, as Elisa already told us, and she introduced the quasisphere by considering the fan of CP1 in a non-rational context, so by considering it as a quasi-rational fan in a quasi-lattice. And so, of course, we can see what happens when we take this data and we construct the foliated manifold and so on. And also another nice example, again with the fun of CP1, is this, and we can prescribe an arbitrary finitely generated subgroup at both poles. So in one case we get the quasisphere, in the other case we get a variant of the quasisphere. Okay, so, and here I just you know, illustrate the construction of the manifold n in these cases. In one case we obtain a Hopf surface, and in the other case, so we get a surface in this case, and in the other case, and this is a consequence of the fact that the rank of the quasi-lattice is much higher, we get a complex compact manifold of higher dimension m+1 that depends on the number of generators. So I think these two examples are interesting because they you know, one can see different phenomena going on there. Okay, so so this is this was already illustrated by Elisa, so I won't say much about this. You can just see the picture when we have the raised generators, the orange raised generators, a blue ghost vector, and we have the dual Gale dual configuration of points and the respective combinatorial data. And one thing that is maybe nice to stress here is the topological type of the leaves that you see when A jumps from rational to non-rational. Of course, the generic leaf jumps from being a compact torus to being S1 cross R. So this is, you can see in examples that you know what happens. So it's nice to see it on concrete and well-known examples. This was worked out also already in Meersseman and Verjovsky in the case of in the, you know, for Hirzebruch, true Hirzebruch surfaces. And how, as Elisa pointed out, the relevant thing here is the possibility to move the slanted ray continuously in this non-rational setting. And we obtain a one parameter family that contains manifolds, orbifolds, and quasifolds. Okay, so let me briefly go on. So these results were mentioned in the last two talks, so I just I'd like to state them here. So I want to, so I remember one of our motivations was to unify the proof, Stanley's proof of the g-Theorem, and so it was quite interesting to get some information on the basic homology of these foliated manifolds. So we consider a simplicial, complete simplicial shellable fan, and to my knowledge, there are no non-shellable simplicial fans that are known. So shellability is quite general as a hypothesis, but so, and of course, polytopal implies shellable. And so we prove here that we compute the Betti numbers of the basic cohomology of the foliated any of these foliated manifolds, and F depends on the pair VT, so it depends on the original starting triple. And so on the combinatorial type of the fan, essentially. And also we prove in the polytopal case, so for a simplicial polytopal fan, that the basic cohomology algebra is generated by classes of degree 2. This is an essential element for the proof of the g-theorem, and I must say that this was the proof of this result is quite involved, and it is the main responsible for the delayed publication of our paper. And so I skipped the proof of these results. And so let's see how we use these informations in order to reprove Stanley's theorem. So we can adapt Stanley's argument in our context. We use basic cohomology of LVM manifolds. Remember, we are considering now the polytopal case. So the first condition, so the first consequence is by Poincare duality on the H vector, we obtain this condition. The second condition, so we want to use the Hard-Lefschetz theorem for basic cohomology, that was proved by El-Qasimi, and for this we need the foliation to be transversally Keller, and this was already known from Loeb-Nicolau and results by Loeb-Nicolau and Meersseman, and the converse is Hiroaki Ishida just reminded us, was proved by him in 2011. So we use this, we apply El-Qasimi's theorem, and we are able to deduce the second condition of the g-theorem, and this on the condition on the H vector. So the g-theorem says that if we have a polytopal fan, the H vector satisfies these three conditions. The first, the second, and the third is, I haven't written in detail, but it's a kind of moderate growth of the coefficients of the H vector, and it's implied by the fact that the basic cohomology of our foliated manifold is generated in degree 2. Okay, so we finally reached one of our goals, which was to give a proof that unifies the three cases. I'm saying three cases because Stanley's original proof was on smooth toric manifolds. Then the same principle can be applied to orbifold, but one has to use intersection cohomology, or there is a proof by Zaffran and Wang that uses foliations. And also, it's it's when you can reprove a result like this, and you have results on the cohomology, and you see that the interplay with the combinatorics still carry over. It means that we have a good model for complex toric quasifolds with these foliated manifolds. And here there's a remark for me, because I told you on Monday something that was wrong. And Dan yesterday just reminded me of something that he had already told me a couple of years ago, that the G conjecture has been solved by Adiprasito in 2018. So these conditions, he proves that the H vector of a simplicial sphere satisfy these exact conditions. So I think the F vector of a simplicial sphere that include also simplicial fans is totally completely characterized by now. But I'm not an expert in this field, so this is. But you know, I didn't want to say something that was not correct any longer. So just to finish, let me just conclude that I propose again this diagram in which we have the triple that was introduced more than 20 years ago by Elisa Prato, and this to this starting datum we can construct a corresponding complex toric quasifold, and then we can give a model for this space by using foliation and all the theory of LVMB manifolds. So we encode this triple in a triangulated vector configuration that allows us to use Gale duality and obtain the right object for the construction of these foliated manifolds. And the manifolds that we get model the complex toric quasifold in the sense that the leaf space is exactly the toric quasifold. So, and let me finish by remarking that in recent years there has been many articles on this developing non-rational toric geometry. We are here in a conference, the whole conference on this topic. So this is great. And so I made an attempt of giving a list of articles where we can find this. We can find a construction that allows to associate to a convex geometric object that contains a fan or a polytope to a complex or a symplectic space or to a family of such spaces. And so here's the list. It's an attempt. Maybe it's for sure is not complete. But anyway, it would be, maybe the bibliography is not updated. I'll be very happy to update it. And it would be very interesting to understand how all these different perspectives are interrelated and also related to the works that Elisa, Prato and myself have presented in our mini course. So now, I show you that I really build on other people's works, and here the bibliography that Elisa kindly passed to me. So I just added a few items. See this, the papers with Dan Zaffran that appear around here. I cannot find them any longer. Anyway, this is it. I'll correct if something is missing. And also, of course, there are, thank you very much, but let me say that there are also, of course, in the bibliography, many related works, but I'll do that second part with more time, and hopefully I won't forget anyone that has contributed with to the, to the history of the subject or to the developments of the subject. Okay, so thank you so much for your attention. And okay, I think I've said what I wanted to say. Thank you.
Thank you to the presentation. Any question?
Was very clear. Thank you very much. Very nice. Frank, if you are around here, I don't know, we still have Frank.
Yes,
Well,
I'm here. Yes. What? Yes.
You mentioned something in the 1920s where there was essentially a moment map in the irrational case.
Well, so yeah. So what happened? So in the 1920s, people in algebraic and statistics came up with something called discrete exponential models, which generalize, like, say, the monomial distribution, which is to the rational normal curve. And in 1963, Birch explained how this expectation map identifies this model with the convex hull of certain vectors. And this is essentially the moment map factors through this such a map. And so I'll explain that.
And then the wars in the late 80s from you are around there, Santiago. So if everybody could send me their big 5 papers you would think be included in
this one by Fiametta. This will be great. So we can put this kind of bibliography at the end of the volume, and this will be fantastic, you know. Of course, we can go back to Euclid, but we'll stop in the 1920s and 60s, you know, I guess. And, well, Attila used to like pointing out that Archimedes have discovered a version of the moment map, didn't he? Attila used to like saying that. That Archimedes discovered a version of the moment map. So great, thank you very much for this very nice talk. And I'll email you reminding you of all these requests. But these references, Frank, would be fantastic to have.
Yeah, I'll probably get them. I'll probably discuss them in what I'm writing, although that I have to worry about the length. But,
yeah, fantastic.
Because it's just, I mean, I found this really fascinating when I sort of ran across this with people in statistics, is that they had something which, I mean, some of them called it the moment map, but it's not really the moment map. But but they recognize it's of the same character, and I thought that was kind of interesting because it's completely independent of symplectic geometry.
Yeah, that's fantastic. And of course, in symplectic geometry, it really comes from physics, where I am coming from the perspective of mathematical physics and geometry and topology, and more algebraic geometry than symplectic. And from this point of view, of course, the moment map is totally motivated by Noether's theorem on invariance. So well, as Alberto Verjovsky likes saying, everything is related to everything.
Everything is interconnected. Thank you, Fiametta. Your talk was beautiful. Grazie tanto.
Let's switch to the last link. Let's switch to the last link.
Okay.
Okay.